ஏதோ ஒன்று பார்த்து சொன்னேன்.
நிறைய வருவாங்க. நீங்க யூடியூப்ல
நீங்க
எப்படி லைவ் எப்படி இத்தனை
யூடியூப்க்கே வந்துருச்சு.
யூடியூப்ல இது நாங்க பேசுனதெல்லாம் சரி.
சார்
சார்
29க்கு ஸ்டார்ட் பண்ணிக்கலாம் இல்லைங்க சார்?
ஓகேங்க.
ஓகேங்க சார், தேங்க்யூ சார்.
ஓகே.
Good morning, sir.
So good morning.
எப்படி சார் இருக்கீங்க? நல்லா இருக்கீங்களா சார்?
Fine sir, fine sir. எப்படி இருக்கீங்க நீங்க?
Yeah, thank you, sir. எல்லாம் நல்லா இருக்கு சார். வீட்ல எப்படி சார்
Happy to
இருக்காங்க?
see you.
யூடியூப் சார். Thank you, sir.
நல்லா இருக்காங்க, நல்லா இருக்காங்க.
சரிங்க சார்.
சார் ஸ்டார்ட் பண்ணலாமாங்க சார்? சார்
ஓகேங்க.
சொல்லுங்க சார்.
சார் ஷால் வி ஸ்டார்ட் சார்?
எஸ் சார்.
ஓகே சார், தேங்க்யூ.
ஓகே, தேங்க்யூ சார். Good morning to everyone. So first of all, I would like to thank.
Sir, 1 minute,
Yes,
sir.
yes.
இங்க அவங்க எல்லாம் ப்ரெசென்ட் பண்ணுவாங்க சார். அவங்க எல்லாம் ஸ்பீச் முடிச்ச உடனே நீங்க லாஸ்டா பண்ற மாதிரி சார்.
ஓகே, ரைட். சரிங்க, அதான். ஓகே, தேங்க்யூ.
ஃபர்ஸ்ட் பிரின்சிபல், தென் கரஸ்பாண்டன்ட், அப்புறம் அடுத்தது நீங்க.
ஓகே, தேங்க்யூ சார். நோட், தேங்க்யூ.
Good morning, participants. On behalf of Arunmurugan College of Engineering, Tharur, I welcome all of you for the webinar on nanocomposites, processing and applications. Now, I would like to invite our principal, Dr. P. Shanmugam, to give the welcome address.
Hello.
Yes, sir. Yes.
Hello. Sir, good morning to one and all.
Very good morning, sir.
Hello.
Good morning.
Morning to one and all. Hello. Good morning to one and all person here. First of all, I
Very good morning, sir.
our very good morning. First of all, I welcome our respected resource person, Dr. Sivasankaran, Associate Professor, Qasim University, Saudi Arabia, for accepted our invitations and ready to deliver the topic nanocomposites, processing and applications for today webinar. I also once again I welcome you, sir. I also extend
Thank you, sir. Thank you.
my warm welcome to our respected correspondent, Dr. P.V. Kandasamy, sir, for helping a lot for arrangement of this seminar. I welcome you, sir. I also extend my warm welcome to our professor and head of the department, Professor Mohan Babu, and coordinators of this webinar, Professor Saravana Kumar and Vijay, and faculty of mechanical engineering for their support for arrangement of this webinars. Once again I welcome all of you for this great sessions. Welcome you, sir. Thank you very much for given the opportunity. Thank you.
Thank you, sir.
Thank you, sir. Now I invite our correspondent, Dr. P.V. Kandasamy, sir, to felicitate the webinar. Sir, please unmute your mic, sir. Your voice is not audible.
My is my video visible?
No, sir. No, sir.
Okay. Now is okay?
Yeah, it's okay, sir. Now.
Good morning, participants. I would
Good
like to
morning.
extend my warm welcome to Dr. Shivashankaran, Associate Professor of Qasim University, Saudi Arabia. I extend my thanks also for having accepted this invitation, and on behalf of college, this COVID-19 situation has made tremendous changes in the teaching learning process around now. Bring in a very good resource person from the foreign university to talk about something which is most relevant and important in this age. I would like to appreciate and congratulate our Arulmurugan faculty team for choosing this topic. I feel that is the need of the hour. Engineering world has given a lot of solutions to problems that have been existing for the decades with the help of nanotechnology. On the other hand, the composite materials with tailor-made properties are manufactured to make it suitable to be used in specific end uses. So by combining these two sophisticated technologies, the nanocomposites, I think this is the material of the future. So every engineer, for that matter, who are pursuing engineering education or working in the career, working in the field, they should be aware of the materials which are going to exist in the near future. And this technology is to be utilized to its fullest extent, because this will solve almost every problem of an engineer in the near future. So once again, I appreciate and I wish this webinar a great success. Thank you for the opportunity given to me. Now the floor is on to Dr. Shivashankaran. Thank you, sir.
Thank you, sir.
Thank you very much.
It gives me immense pleasure to introduce our resource person, Dr. S. Shivashankaran. Dr. Shivashankaran, sir, is working as an associate professor, Qasim University, Saudi Arabia. Sir has completed ME degree by securing GATE score with All India ranking of 155, and also doctoral degree both from prestigious institution, National Institute of Technology. Sir is having more than 19 years of teaching experience in India and abroad. Sir has published 79 international journals and completed 11 projects sponsored by various funding agencies with the cost of around 1 crore and 72 lakhs. Sir has written one book on nanoparticles and has edited 3 books. Sir is a reviewer of various international journals. Sir is a lifetime member of various technical societies. And now I would like to invite our resource person, Dr. S. Shivashankaran, sir, for this webinar.
Thank you, sir. Thank you very much for the nice introductions. So first of all, I would like to thank the management, the correspondent of Arulmurugan College of Engineering, and I would like to extend my thank to the respected professor and the principal of Dr. P. Shanmugam sir, and the Department of Mechanical Engineering faculty members, so who have given some good opportunity for me. So first of all, I would like to wish you and good morning everyone. So my topic, so today we would like to discuss related to the topic of nanocomposite materials. Okay, nanocomposite materials, it's not that much new. Even 10 to 15 years before it was new, and now majority of the products, so majority of the products are being produced and coming to the market, and from in the name of nanomaterials, okay, nanomaterial as well as nanocomposites. Okay, so both are playing the major role nowadays in the market, and most of the products are being produced from the nanomaterials and nanocomposites. The application wise very vast. Okay, so even I know from the nano level or nanoparticle level or nano composite material unimaginable properties can be obtained, can be achieved. Okay, so you know very well the name itself. Okay, the name itself, it indicating nano mean what? The particle size, any one of the dimensions. So the particle size or the grain size, okay, maybe the nano level. Okay, 10 to the power of -9 meter. Okay, 1 trillionth of meter or 1 millionth of millimeter. Okay, that is what the nanometric dimensions, nanometric scales. Okay, fine. And the topic is nanocomposites, processing and applications. So processing and applications. Right. Composites. So the composite be nothing but combination of two phases. So basically, there are two phases present in the composite material. One is called primary phase, and the second one is called fiber phase or secondary phase. The best example of composite is our human anatomy. We take our for example for our hand. Okay, is the minimum consisting of a bone. Okay, and then the skin tissues. Okay, here the bone will act as a fiber phase. Okay, that means secondary phase. So whatever the load I want to apply it, okay, and most of the load and stresses will be absorbed by the bone only. Okay, but without skin, that means without matrix, the bone cannot able to withstand any supporting load. Okay, therefore it needs to connect the fibers. Okay, therefore we need another phase which is called matrix phase. Okay, this is what a composite. So composite means consisting of two phases. Okay, namely primary phase, matrix phase, and secondary phase, fiber phase. Okay, and these two phases are physically distinctive. Physical properties of the two materials will be different, and chemically it will never insoluble, it will never dissolve. Okay, that's why it is called composites. Okay, two or more materials which are physically distinctive and chemically insoluble, it will never dissolve together. Okay, so in order to obtain some desired properties. Okay, otherwise we can say it is called alloy. So alloy is completely different from composites. Okay, fine. In nanocomposites, so any one of the particle size, okay, of the fiber or matrix may be the nano level. That's why we can call it as a nano composites. So now there are many nanocomposite materials out there. Basically, you know very well the classification of engineering materials. Okay, so metals and alloys. Okay, and then second category ceramics. Okay, and then the third category, okay, polymers or plastics, and the fourth one is called composite nowadays. Okay, right. Anyway, from the metals we can have some good strength. Okay, ductility. But even though the high expected strength cannot be obtained, expected modulus of elasticity cannot be obtained. And second, in the case of polymers, plastics, okay, very lighter in weight. Okay, density can be minimized, but very poor in strength. Okay, and in the case of ceramics, it can exhibit high modulus of elasticity, but very poor in ductility. So in order to achieve the combination of these two composite materials are being developed. So that means the mixing of metals alloy or some polymers or some ceramics. Okay, fine. So let us discuss one by one. Right. This is our outline of our today presentations. Hardly I will take 1 hour maximum, or 1 hour 5 minutes or 10 minutes. I would like to complete within time. Okay, fine. So introductions about the nanomaterials, nanocomposites, and what are the potential applications of the nanomaterials and nanocomposites, and the introduction about the composite material and nanocomposite materials, and what are the challenges, issues the researchers and the industry people are facing during synthesizing the nanocomposite material, which we are going to discuss. And then the processing methods, what are the novel processing methods for fabricating the polymeric matrix nanocomposite. Okay, there are 5 novel methods out there. Okay, whenever we want to develop polymeric matrix nanocomposites, there are basically 5 novel methods, namely solution casting, okay, melt blending, okay, and then in situ polymerizations, okay, and electro depositions and electro spinning. These are the 5 principal processing techniques are there by which people are developing a lot of nano composite material. This what we want to discuss it today. And then finally, I want to give a short glimpse of introduction about the mathematics and ceramic matrix composite. This is a very ocean topic. Okay, within an hour, I would like to try to do my level best, and I would like to share my experiences. Okay, anyway, I am working on the mathematics based nanocomposites, and little work I have done for the polymeric matrix nanocomposites. Even I want to, as per the given topic, okay, I want to share these contents within a couple of within an hour. Okay, fine, right. So what are the properties? So you know very well. So whenever the particle size, okay, whenever the particle size are being reduced under nano level, okay, so it will completely change the chemical, okay, physical properties of the material. That's why, okay, all the nanomaterials, okay, nanocomposites are producing or exhibiting extensive, okay, interesting or unimaginable behavior, unimaginable properties, okay. Sorry. Right. So whenever you want to reduce decreases the either grain size or the particle size, okay, both are different. Even whenever you want to synthesize mean developing a methods to fabricate the new materials. Okay, so whenever we want to synthesize or decreasing the particle into nano level or the grains into nano level, for example, and the bulk metal, whatever the aluminum, steel we are seeing, all are bulk metal. Okay, usually the grain size will be very big. The coarse grain will be formed. Okay, so by means of some latest techniques, whenever we want to decrease the grain size, okay, by solid state method or any methods, okay, the surface energy will be increases. Okay, so because of the surface energy present in the nanomaterial, it is completely changing the material property. That means my point is, whenever we want to decrease the grain sizes or particle sizes under nano level, both the physical property will be changed, mechanical, electrical, chemical, and optical properties will be changed. Okay, fine. For examples, this slide. So let us take here gold. Let us take here gold. We know very well. Okay, so highly expensive metals. Okay, and it is exhibiting a yellowish color in the normal room temperature, normal conditions, conventional conditions, or even whenever you want to reduce into a thin foil, like 1 centimeter long foil, still it can exhibit yellowish in color. Fine. So further, if you want to broken the foil or the gold into small and small nanoparticles, okay, the color of the metal will be completely different. Okay, it will be completely different, and it will no longer exhibiting the property like conventional gold. Okay, for example, let us take whenever we want to reduce the particle size of the gold around 50 nanometer, it will exhibit blue or purple color. Okay, and whenever the particle size of the gold under 25 nanometer, it will exhibit red in color. Okay, and 1 nanometer mean it will exhibit some orange color. You see, so the particle size keep on decreasing mean it is completely changing the chemical properties of the material. That's why all the nanomaterial, okay, and nanocomposite material are producing extensive properties. Okay, so fine. And and one more thing, okay, for example, the same gold, okay, so whenever we want to decreases the particle size and the nano level, so at least 50% of the melting temperature can be decreased. Okay, for example, conventional copper or conventional gold, whenever we want to melt the gold, we need to heat 1064 degree centigrade. Suppose if the gold and the nano level mean, okay, 532 degrees centigrade is enough. Okay, fine. So that is the beauty of nano materials as well as the nano composite materials. Okay, fine. So under nanometric scale, okay, all the properties will be improved, especially for the gold. Okay, so because of presence of large surface area, okay, it will act as a high reactivity. Okay, therefore the gold nanoparticle can act as a best powerful catalyst converter. Okay, fine. And nanotechnologies, as we discussed little bit above, Okay, any device or machine or any product or any process, if it is involving or the matter composed of any one dimension is a nanometric level, mean we can call it as a nanotechnologies. So roughly the size of the particle or the grain size is, okay, the matter size is, if it is starting from 1 nanometer to 100 nanometer, mean then the device or the machine we can call nanotechnologies, produced from nanotechnologies. Right. So this slide is indicating, okay, this slide is indicating different types of nanomaterials. Okay, for example, you see this is the gold nanoparticles. Okay, and different things, and this is what the buckyball. Okay, it is producing a lot of extensive features. Okay, so it is liking a ball or even sometime tube form also available. Okay, it is a produced from carbon only. Okay, carbon you know very well, like iron. Okay, the carbon also allotropic metal. Okay, material. Okay, it will exhibit a different behavior with respect to different temperature. Buckyball or sometimes tubes. Okay, so this kind of shape, this kind of forms will produce or will produce lot of electrical connectivity and many things. Okay, many interesting features can be obtained from the buckyballs. And you see the third picture is representing the SEM images of iron platinum nanosphere. Okay, nanosphere. And let us see, you see the bottom one. Okay, bottom left. So this is the titanium nano flower form. You see the titanium, and when we want to decrease the size, it is exhibiting flower form. Okay, and this is a silver nanoparticle. It is exhibiting cube. It is exhibiting cube, and this is what tin oxide nano powder. It is exhibiting also like a flower. The point is, okay, so whenever we want to decrease the particle size and the nano level, okay, so each material depends upon the processing methods, depends upon the conditions which we are using during synthesis. Okay, the shape of the particle will be different. Okay, that's what the things. And this slide, the scale, what is the scale matter? Okay, and you see usually the average height of the man 1.1 meter, we can able to see our naked eye. And then for golf ball, the average size of the golf ball is 4.2 centimeter, and the fly we can able to see our naked eye. Okay, yeah, that is enough. And the dime or some bacteria, okay, or some insect, you sometimes we can able to see, or we can, whenever we want to see its behavior, we can use some light microscope. Okay, we can use some light microscope. So up to 1 millimeter, okay, we can able to see, okay, from a naked eye. Whenever the particle size or any materials lower than 1 millimeter, we cannot able to see clearly from our naked eye. So for which we have to go for some microscopes. There are two microscopes are there. Either light microscope can be used or electron microscope can be used. Okay, so light microscope means, okay, so up to 1000 x magnifications or up to 2000 x magnifications. So we can hardly 25 1 centimeter level, 25 micrometer level, we can able to see clearly. But when you go to the, for example, some other red blood cells, whenever we want to examine the behavior of red blood cells, or whenever we want to see the behavior of a red blood cell or some bacteria, nanoshells, okay, some virus, DNA, okay, or the carbon nanotubes, okay, so we cannot able to see using either light microscope, So in that case, we have to use electron microscopes. Basically, there are two electron microscopes are there. Okay, namely scanning electron microscopes, and the second one is called transmission electron microscopes. Okay, all these electron microscopes are being operated under pure vacuum only. Okay, high velocity electron should be passes over the sample, by which many internal features of the sample can be examined. Right. And this slide is indicating what are the classifications of nanomaterials. Okay, so there are many different, depends upon the size, depends upon the dimensions. So they have given different names. One is called zero-dimensional sphere, zero-dimensional nanomaterial. That means like a dot, almost the diameter is negligible. Okay, all the quantum dots, maybe that size around lesser than 1 nanometer. Okay, so we can call it as a zero-dimensional sphere. Okay, or cluster. Usually, whenever we want to decrease the particle size and the nano level, lot of surface energy will be created. Okay, because of presence of the more surface energy, okay, and all the particles try to attract towards each other, okay, because of van der Waals force of attraction. That is called clustering or agglomeration. This is a major issue whenever we want to synthesize or use the nano material, or whenever you want to dispose the nanoparticle over the any matrix. So the dispersion of the nanomaterials are very important. Actually, it will be very highly challenged. Okay, we will discuss one by one for the coming slides. And the second one is one-dimensional nanofiber. Okay, may having length only. Diameter will be neglected. Nanofiber or wire or rod. Okay, and then the third one is called two-dimensional nanofilm, having length and width. And the last one, the bulk form. Okay, that means three-dimensional form. Both the length, width, depth, or diameter, like a sphere, can be appear. Okay, so the usually the size 25 to 100 nanometer for the three-dimensional nano material. Okay, this is the different according. Suppose the buckyball examples of zero-dimensional sphere nanomaterial, and the nanotube is example of one-dimensional nanomaterial. Here the diameter is very small, that so it will be neglected. Only people are accounting the length only. And two-dimensional graphene having length and width like a single layer, okay, which is called two-dimensional graphene. And the third one is called graphite. It will appear like a layered structure. Okay, right. So this slide is showing the applications of the nanomaterials. For example, the one-dimensional like a disc or dot. Okay, for example, this slide, and the nano clay. So the nano clay is acting as a best barrier property. It can able to absorb all the oxides, carbon dioxide, anything like that. Means it can act as a filtering agent. Okay, so this one-dimensional, most of the one-dimensional nanomaterial can produce barrier properties wherever we want to minimize the heat transfer rate, okay, or whenever we want to absorb the odor in the water or air, okay, we can use one-dimensional nanomaterial. And the second one is called two-dimensional nanomaterial. Example, carbon nanotubes. Okay, so this is the arrangement of the carbon fiber. Okay, and this is the random orientations. So different size, different forms are there. Okay, there are many nanotypes are there. But basically there are two types of nanotubes are there. Single wall carbon nanotube, multi-wall carbon nanotubes. Okay, and all these nanotubes, when we want to mix, even for our household appliances, even for whenever you want to construct a building, we can mix some of the carbon nanotube for to the concrete, and by which the strength of the concrete will be improved. Not only the strength, okay, whenever something happen, whenever the load is exceeding greater than some value, okay, so crack may appear over in the matrix. Since the presence of nanotubes, okay, nanofiber, okay, it will try to restrict or arrest or slow down the crack propagations. So that is the benefit we can obtain from the disposing the nanofiber nanotubes for the give any matrix material in the case of composite. And then third one, okay, usually the three-dimensional nanomaterials. Okay, three-dimensional materials, right? Silicon dioxide, titanium dioxide, zinc oxide, cerium oxide. Okay, so mostly all the ceramic, all are ceramics. You know very well. Ceramic mean what? Made up of oxides, carbides, nitrides, borides. So whenever you want to synthesize a nanomaterial from ceramic, mostly, okay, the shape and size of the ceramic nanoparticle will be sphere form or cubical form or some polygonal shape, okay, will be obtained. Okay, that's what the SCM image showing. And these nanoparticles can be easily disposed for any metal or any polymers, okay, right, or even any ceramic. So we can produce a composite. So by which the point is all these three-dimensional nanoceramic material, okay, or best example for mechanical reinforcement. So by which the strength of the material, mechanical properties can be improved, and the scratch resistant, wear resistant will be increased, and it will try to minimize or it can increase the fire resistance. That is called flame retardants. Okay, fine. And you see, this is this slide indicating what are the types or forms of nanomaterial. So as I already we have told, basically the nanomaterials available in the form of particles, nanoparticle forms. This is the nanoparticle forms, okay, or quantum dot. You see, in a single nanoparticle, inside the nanoparticle, okay, there are n number of quantum dots will be there. N number of quantum dots will be there. Please understand, even nanomaterial, nanocomposites almost saturated. Okay, now from beginning, okay, now and even the future, okay, the research will be completely based on quantum mechanics, quantum dots. There are a lot of scope. Even those who wish to start your research career, you can please focus on quantum mechanics or quantum dots. Okay, so people are starting the research because extensive properties, especially for for sorry um, sorry, thermality material, especially for thermality material, this quantum mechanics, quantum dots is playing a major role. Okay, in order to convert the sun and solar energy, okay, from light and heat into electricity directly, thermolytic materials are being play a major role. And not only for that one, it will use as a yeah, that means waste. Sorry, these material can act as some waste heat recovery system. Okay, so for which the quantum dot this technology is playing major role nowadays. Okay, and then the third one is called nanoshell. Okay, nanoshell is also for biosensor. For example, this is a gold. It is inside the gold. Okay, there is the silicon dioxide. Okay, this nanoshell will sense the human behavior, okay, temperature or whatever it may be. So this nanoshell can be used for the sensor applications. And another form is the rod form. This is the image for the gold nano rods. Okay, and this is a nano wire. Okay, and this is a film. Very maybe 1 nanometer level thickness or 2 nanometer or 10 nanometer. Okay, this is the nano layers. Okay, so these are the different forms of nano materials, right? Next, we should know how can we synthesize a nanomaterial or nanocomposite material. Okay, this is a slide is representing. So basically, there are two approaches are there, namely top-down approach and bottom approach. Okay, bottom approach mean like a construction of building from A to Z. Okay, so we have to dig the foundation. We have to form the foundations, constructing the walls like that. Okay, and top down mean from top to down. Okay, right. So in the bottom approach, people will synthesize the nanomaterial by assembling. Okay, by assembling all the atoms together. You know very well, all arrangement of atoms will make one molecule. All arrangement of molecules will become clustered like a particles. Okay, we can synthesize nanomaterial. In the case of top down ball milling, okay, many techniques are there. Okay, we have to, like olden days, even whenever we want to have some rock, okay, we have to engrave, okay, shape from the hill, okay, from the rock. Okay, that is called top down approach. These are the two approaches are there, so by which we can synthesize the nanomaterial and nanocomposite material. And you know very well, we should know why the nanomaterial or the nanocomposite material exhibiting interesting future. What are the scientific phenomena? We should know. Basically, there are the main root cause. There are two reasons of that. Okay, because of these two reasons only, all the nanomaterials, nanocomposites, okay, are producing extensive has extensive properties. Namely, surface area to volume ratio will be high. Surface area to volume ratio for the nanomaterials are very high. That's why, okay, we can able to get extensive property. Okay, so how can we see how can we know the surface area to volume ratio? You see the figure, and this is a conventional material, bulk material. Okay, first let us take some cube having some volume. Okay, for the same volume, whenever we want to broken the material into nanometric level, more grain boundaries, more contact area will be formed. Okay, this is what the surface area. So when compared to this sample, okay, here more large number of surface areas are forming for the same volume. Therefore, the surface area to volume ratio will be increased extensively. Because of this one, all this nanomaterial will have lot of reactivity. Okay, and that's why we can able to get improved property. This is what this sketch or this plot showing surface area to volume ratio with respect to the particle diameter. As long as we keep on to decreases the particle size and nano level, you see after reaching certain level, the surface area to volume ratio will be increased drastically. Okay, so because of the presence of surface area to volume ratio, okay, we are getting interesting features. And the second one important root cause scientific phenomena is the quantum confinement. Okay, quantum confinement, the space occupied by the atoms will be very small. The space occupied by the particle and the space occupied by the atoms will be very small. So because of the quantum confinement, okay, so when we synthesize a nanomaterial, okay, so the all the electrons, okay, will be entrapped, okay, cannot able to move. For example, you see this picture, okay, it is a large size of the particle, and this is the quantum dot or nanoparticle. So whenever keep on decreasing the particle size, the energy, the band gap, okay, the band gap mean the energy gap. The energy gap mean what? You know very well. All the elements, metallic element or any material composed of atoms. All the atom consisting of nucleus and electron. The electron will be revolving surrounding the nucleus. So inside the nucleus, we know very well. Okay, inside the nucleus, we know there will be a proton and there will be a neutron. Okay, and one more thing, all the electron will revolve over the orbital, and some of the elements, some of the orbital having some valence electron. Okay, some of the orbital will act as a conductive band. So whenever we want to decrease the band, whenever we want to decrease them nanoparticles, okay, the gap between the conductive bond, okay, and then valence electron band will be increases. Okay, therefore the electron cannot able to move freely. Okay, that's what the word trapping of electron. That's why all the nanomaterial will produce lot of the energy gap will be very high. That means the energy absorption, when you see this curve, it will become narrow. It will become narrow. That means the energy band gap for nanomaterial will be very high, due to which the nanomaterials are producing interesting phenomena. Okay, so what you understand now? So the main features obtained from nanomaterials are two things: because of surface area to volume ratio, and then quantum confinement. Confinement. Okay, right. And then applications. So there are a lot of applications of nanomaterials, nanocomposites, textiles, smart cloths. Nowadays, smart cloth means what? Self-cleaning cloth. So people are coating some silver nanoparticle or nano gold particle. So by which, or nano titanium dioxide. Okay, by which, whenever the stain is present or water is Hello. So can you able to hear my voice, please? Anyone?
So you are able to, yeah, we are
Now
audible.
only it is getting connected.
You are audible.
Okay, fine.
We are audible.
Right. Okay, fine. Good. Yeah. Sorry for the interruptions. This will happen. It's common. Right. So we will continue on our topic. So we are the application wise, it's very vast. Okay. So my point is, even nowadays, nano smart clocks are there. Okay. Self cleaning windows are there. Okay. So even folding mobiles are there. So the application very vast: textile, biomedical, healthcare. Okay, electronics, environmental, environmental applications. Okay, everywhere people are using the nano materials. Okay, fine. We will discuss one by one. I will show you some interesting one. And for example, electronics and communications. Okay, so nowadays we are having interesting LCD screens. Okay, and okay, so all are produced from nanomaterials only. So you see, the olden days, 1990s itself, they use some amorphous silicon. Amorphous silicon will never have transparent nature. Okay, so then people invented polycrystalline silicon. Okay, so it becomes transparent. Then they used indium, indium, gallium, zinc oxide. Okay, so that's why we can able to get interesting devices, electronic devices. Okay, and people are developing many new nanomaterials and for the electronic and communications devices. And you see, people are using some silver nano wire. Okay, over polyethylene dioxide okay, so this is a polymer. Okay, so using this OLED material, okay, so we can able to produce folding. We can fold the mobile tab or a laptop, anything. Okay, so these are the new things. Everything can be achieved from the nano materials. Okay, fine. And even for structural engineering applications, okay, for even the construction industry, okay, even for the construction industry, people are using the nanomaterial. They are adding the nanomaterial. For examples, okay, the concrete. For example, the concrete, they have added some nanotitanium dioxide, okay, carbon nanotubes. So therefore, the increase we can able to increase the strength of the concrete. You see this picture, okay, the graph is showing compressive strength versus different weight percentage of carbon nanotubes. Okay, this indicate ultra high pure concrete. Okay, and when we keep on increasing the carbon nanotubes, okay, even for 0.5 percentage of carbon nanotube, improved strength extensively. Okay, if you keep on increasing further, it starts decreases because of some agglomeration, clustering. That's why whenever you want to synthesize or whenever you want to fabricate nanomaterial or nano device or nanocomposites, the dispersion is very, very important criteria. Okay, the dispersion is a highly challenged one. So which method we are going to use it accordingly, the dispersion efficiency will be different. So as long as if we have a proper distribution, uniform distribution of the reinforcement, uniform distribution of the nanoparticle for the given matrix, then we can achieve extensive properties. Unless the properties will be decreased. Okay, fine. And you see, even you may have a doubt. What is the strength that much improved? Maybe small, but the failure. You see, for example, this is a SEM image for the same concrete mixed with the different percentage of carbon nanotube, 0.5 percentage of carbon nanotubes. Okay, this is a matrix. Okay, and this is a magnified view. This is the image taken at lower magnifications, and this is the image taken at high magnifications. Okay, so the moment if you apply the load keep on increasing, the crack will propagate. Okay, but since the presence of carbon nanotube fiber, okay, CNT fiber, it will try to arrest the crack propagations. It will try to arrest the crack propagation or slow down or diminish or decrease, okay, or slow down the crack propagations for the matrix material. Therefore, the life of the product will be increased. Okay, that single carbon nanotube maybe this is a figure indicating single wall carbon nanotube, and this is a multi-wall carbon nanotube. Anything can be used. Okay, for conducting application, people are using single wall carbon nanotube. For dispersion, people are using multi-wall carbon nanotubes. And one more example, I told you already, self-cleaning windows. Okay, even whenever the water is coming, falling, or rain drops are falling over the windows. Okay, nowadays the smart windows, okay, coated by the nano titanium dioxide. The moment it gets water, okay, it will react with this nanoparticle, nano titanium dioxide, will react with the water, and it will convert into very thin transparent layer. That's why even water falling, we cannot able to see anything. Immediately it will and then the presence of nanotitanium dioxide particle will try to make into thin layer, transparent layer. And one more thing, the smart windows, okay, smart glasses, okay, during sunny days, okay, so the smart windows cannot enter the radiations, so we cannot feel any heat, hot. Okay, that is the benefit of smart glasses. Okay, and it will act as a dark. Whenever there is a cloudy days, okay, the same glasses will become act as a lightening. Okay, some heat can able to come inside the houses. Okay, to have some average temperature. Okay, this is the benefit of nanomaterial for the real time applications. And even for nowadays, the painting, fire resisting coatings, people are using for the structural application. And therefore, unknowingly something happened because the fire mean the structure cannot be failed. Okay, and fire can, that means the fire resistant coating can able to withstand high temperature. Okay, that is the benefit. So these things can be obtained from nano material. And one more interesting is aerogel. Okay, aerogel insulations are using nowadays. Okay, it will act as the best insulations. Okay, whenever we want to place, okay, paste the aerogel in the wall, it will never allow the heat from the air to the room, so we can feel some comfortness. Okay, why, how? Okay, when you absorb the aerogel is nothing but silicon nanoparticle. Okay, so the aerogel, inside the aerogel there are a lot of pores will be there. That pore will act as a vacuum. So that means inside the pore there are vacuum will be there. Okay, this pore will act as a vacuum, and due to this one, the air, okay, the temperature cannot transfer from surrounding to the another side. Okay, that's why this aerogel is nowadays acting best insulations. Okay, fine. And another application is medical application. So this nanotechnology, nanomaterials, it is a boon for the medical field application. Actually, for medical field only, people they have developed many nanomaterial, but nowadays people are using in all the field of engineering. Okay, and for example, in the medical field, examples. Okay, for gold, when people are coating some gold nanoparticle attached over the DNA, by which they can send into the human organ. It can able to sense, it can able to detect the sequence of genetic genes. Okay, so by which we can examine that the doctor can diagnose something. Okay, for the human beings. And even for band-aid. Okay, nowadays the smart band-aids coated by some silver nanoparticles. Okay, so since presence of silver nanoparticles, okay, so whenever we want to have any wounding, okay, so it can able to heal quickly. Okay, that means since the presence of nanoparticle, okay, it will never allow the any infected viruses inside the body, organs, tissues. Therefore, okay, we can we can cure, we can get the relief from the wounding quickly. Okay, so that is the benefit of nano materials. Okay, and for energy applications, see this slide is indicating energy applications. Okay, right. So even for extracting the heat, okay, I got some feedback, and if you have any doubt, please at the end of the lectures we can share. Okay, we can make some discussions. Right. So whenever we want to extract the hydrogen gas from the water, okay, or harvesting the energy from the sun, okay, nanomaterials are being used, okay, nowadays, okay, for hydrogen fuel cells, batteries, and lithium-ion batteries, capacitors, okay, nanomaterials are using it, okay. And for example, a simple photoelectrochemical cells, okay, is usually composed of titanium dioxide and platinum. Usually we know all the cell, energy cell, having two electrodes. Okay, one will act as the anode, the other will act as the cathode. Okay, usually the nano titanium dioxide will act as a anode, and the platinum will act as a cathode. So these two electrodes are usually immersed in the water. Okay, we want to produce our hydrogen gases. So whenever the sun from the solar heat, based on the heat obtained from UV solar, okay. So whenever the water exposed heat from the solar, okay, the nano titanium electrode will react with the water. Okay, it will produce a lot of oxygen. It will separate the oxygen and hydrogen, usually oxygen. Okay, and it will produce a lot of holes, photogenerated electrons or photogenerated holes. This photogenerated electron will go to the platinum electrode. This platinum electrode, okay, can able to help to produce the hydrogen. There are some other nanomaterial by which we can separate, okay, oxygen as well as the hydrogen gas separately. This is what the application of nano materials. Okay, another one, okay, for minimizing the pollutions, for filtering application, people are using nanomaterial. For example, this carbon nanotubes, okay, some polymers, okay, adsorption for adsorption applications, okay, not absorption. Absorption is completely different than adsorption. Adsorption is the best technique for filtering the gases or filtering the water, okay. And the nanoclays, activated charcoal, carbon foam, graphene, all these materials are being used for filtering applications. Okay, how? Because of the presence of pores, it will never allow the unwanted metal or oxides, nitrites, or some bad gases. Okay, so that is the benefit of nano material. Even this is the nano tubes or nano aluminum oxide can be coated over the membrane. Okay, so for which we can use water filter. Okay, so all the water filter systems, people are using nano materials. Good. Now come to the composite. So already we have discussed composite mean having two phases. Okay, so one is called matrix phase, another one is called fiber phase. That fiber phase may be a continuous fiber, okay, or chopped fiber, or viscous, okay, or particulate. Okay, there are four forms or common fibers shapes. Okay, fine. So examples of composite: natural composite, wood. It is composed of cellulose and lignin. Okay, and hydroxyapatite, the bone composed of natural composite, biocomposite, hydroxyapatite, ceramic, collagen, like tissues, matrix. Okay, and then silicon carbide, aluminum oxide, ceramic composite, magnesium oxide, iron, mathematics composite, polyester, titanium dioxide. So polyester will act as a matrix. Okay, polymeric matrix composite. Here iron will act as a matrix. Okay, fine. So my point is, so composites is consisting of two phases: fiber phase, matrix phase, and so we can have the composite. And yes, we should know what are the functions of matrix material. Okay, the main functions of matrix is, okay, in order to transmit the load, okay, from between the fibers or from external to the fiber, okay, or among the particles, matrix are being used. Okay, so matrix usually ductile nature, soft in nature. Okay, fine. Further, in order to arrest the crack propagation, maybe due to some extent, some unavoidable things, or because of overload, one fiber may broken. Okay, between the fiber, let us assume there are n number of fibers are arranged vertically. Between the fiber, there are a lot of matrix, skin, not skin, some tissues or some soft. Okay, so one fiber is broken mean, okay, because of since the presence of the matrix between the fiber, the matrix can able to avoid the propagation of crack from one fiber to another fiber. That's why we can get the okay, so that is the main functions of the matrix. Okay, and further, please understand, the matrix material will never carry the load. Of course, maybe 5%, 10% of load may carry, depends upon the strength of the matrix, but majority of the load, majority of the stresses will be absorbed by the fiber material only, ceramics only. And further, the matrix, okay, can able to help to orient, to hold the fibers or particle in a proper orientations. Okay, and further, because of the the skin, we can able to protect the bone. Like that, the composites, okay, the matrix can able to protect the fibers or particle from the environment, by which some oxidation, okay, some unusual things we can avoid it. Okay, fine. And functions of the fiber. Already I told the main purpose of the incorporating the reinforcement. The main purpose of incorporating addition of the reinforcement, okay, is to absorb the load from the matrix. Okay, so that by which the strength of the material will be increased. Okay, so that is the main aim. That's why people are using this composites. Okay, fine. And yeah, you see, this is a conventional layered composites having some plastic polymers, some carbon fiber, okay, something, okay, some fiber, okay, some laminate composites. If you introduced some aligned carbon nanotubes, okay, between the matrix, okay, so that will try to minimize or arrest the crack propagations. Okay, that is the benefit of adding some filler, nanofiller, or nanofiller or CNTs. Okay, this is the picture showing carbon fiber. This is a magnified view. Okay, so you see, whenever the carbon fibers are present between the matrix, between the polymer matrix, okay, the crack will be arrested. So the strength will be improved. And why we have to go for composite material? We know very well. We can get extensive properties. Okay, we can get extensive properties from the composite material. You see, this is the Ashby material chart. Okay, so tensile strength versus Young's modulus. Tensile strength versus Young's modulus. And you see, and the composites, we can have more tensile strength and then Young's modulus value. And similarly, this is another chart which is relating the fracture toughness versus tensile strength. We can obtain good fracture toughness and tensile strength. The main purpose of going for composite material is to have to obtain more in fracture toughness. That fracture toughness will improve the life of the component. Okay, the fracture toughness define the creep resistance, the long life of the component, the material. That's why people are using composite. And all the aircraft structure, spacecraft structure, okay, marine structure, usually made up of composite materials. Okay, composite material. And whenever we want to design the any material for mechanical components, okay, any product, okay, as engineers, we should know the ratio between Young's modulus of elasticity over density of the material. E by rho is very much important. This is a important criteria, important factor we have to follow during designing the many material for the product. Okay, this E by ratio should be high. Then only the particular product life will become high. Okay, so that means what? Whenever you want to select a material, it should have high strength but lower in density, lower in weight. Therefore, this E by rho value can be obtained extensively from the composite material. That's why it is exhibiting extensive properties. Okay, and of course, this is a picture showing the relation between density, okay, with respect to different material. You see metal. We know very well metal have high strength, but the drawback is higher in density. Okay, higher in density. Whenever the density increases, the weight of the component will be increased. Okay, so it will consume a lot of energy. Okay, no use. And ceramic, of course, average density, but of course, there's all the ceramics are having good in Young's modulus value, but okay, it will exhibit very poor in ductility, especially very poor in for tensile load. Okay, that's why most of the even tiles and most the column, all the ceramics, okay, all the ceramics should be always subjected to compressions only, not for tensions. Okay, and when we see the polymers, of course, very low in density. Okay, that means the product made from the polymers and the weight of the component will be minimized. But the problem is, okay, very poor in strength. Therefore, people developed in the composite material. Sorry, we can obtain average good in the density also can be minimized, but the strength and stiffness can be minimized. So please understand, from the composite material, the strength to weight ratio, the stiffness to weight ratio, the creep resistance, okay, and the corrosion resistance, okay, so major properties can be improved via the composite material. Okay, fine. And next, so this slide is indicating the what are the classifications of composites based on the matrix material. Okay, so in order to improve the properties of any metals, metal mean what? Iron or aluminum or magnesium or titanium. we can introduce some ceramics, aluminum oxide, silicon carbide, boron nitride, titanium carbide. This is examples of metal composite. In order to improve the properties of ceramics, you know very well, ceramics producing a lot of Young's model value, poor in ductility. But now the modern ceramics can produce even super plasticity. Nowadays, modern ceramics can able to produce super plasticity. Okay, good in plasticity. Okay, so the mixing of ceramic phase over the ceramics can able to improve the the ductilities. Okay, that's what ceramic metals composite. And to improve the properties of plastics, polymers. Okay, either thermopolymer or thermoset polymer or elastomer, we can add some of the reinforcements. Okay, that is called polymer matrix composites. Either we can add carbon or glass, okay, or boron. Okay, examples of polymer matrix composite. And the fourth one is called interesting one, intermetallic composite. Okay, so when we see the first three composites, majority of the composites, all the reinforcements are readily available. We can mix it together. But in the case of intermetallic matrix composite, during synthesize the material, during synthesize, okay, during manufacturing the material, okay, depends upon the addition of the reactant, surfactant, okay. So some of the reinforcement will be formed. Some of the reinforcement will be formed over the matrix material, which is called intermetallic composite. Iron aluminum can be formed, iron aluminide, okay, nickel aluminide, titanium aluminide. Usually these phases will form during heat treatment. These phases usually form during heat treatment, okay, of the alloy. And next, classification of the composite based on reinforcement. Okay, maybe the fiber strengthened composite or particulate composite, okay, or flake composite. These are the different shapes of the reinforcement. Okay, so the fiber strengthened composite means the length of the fiber. Okay, if the length of the fiber is 0.1 to 250 millimeter, we can then the majority of the load will be carried by the fiber only. Okay, that's why it is called fiber strengthened composite. One more point is, okay, whenever we want to prepare the composite material, the mixing, the ratio between the matrix to reinforcement is very much important. Maximum 60 to 70% of the fiber material only can able to mix properly over the matrix. At least 20 to 30% of matrix should be provided in any composite. Okay, right. My point is, in the case of fiber strengthened composite, okay, since the fibrous length is very high, okay, just we need to join the fiber. That's why 30% of matrix is enough. My point is, the fiber strengthened composite up to 70% of fiber can be mixed with the matrix. Okay, in the case of dispersion strengthened composite, okay, here the diameter of the particle fiber is starting from 10 nanometer to 100 nanometer. Okay, so for this one, because of nanometric level, okay, the volume fraction maximum we can go up to 15% only. Beyond 15%, we can add, but we cannot get improved property. Okay, when we add the nanoparticle beyond 15%, okay, the mechanical property starts to deteriorate because of clustering, because of agglomerations. Okay, right. But nowadays, even it can be overcome by some latest techniques. Okay, fine. And the third one is called particle strengthened composites. So here particle mean the diameter of the particle will be greater than 1 millimeter. So in that case, we can add the ceramic particle up to 40%, so that property will be improved. Anyway, among this composite, dispersion strengthened composite can increase strength of the matrix material. Okay, fine. And the other one is, when we want to prepare the composite material, the orientation is important. Okay, for example, sometime the fiber will be oriented along only one direction, either 0 or 90 or 45 degree. So in that case, the composite material will produce anisotropic characteristic. So what do you mean by anisotropic? That means whenever we want to apply the load along the fiber orientations, okay, the material can able to withstand the load. Suppose if you want to apply the load perpendicular to the fiber orientation, that is along y direction or along z direction, okay, so the property will not be obtained good. Okay, that is called anisotropy. The second one is called planar based composite. Okay, here the fiber will be arranged 0, 90 degree orientation. Therefore, the load should be applied either along 0-degree orientation or 90-degree orientation in the real time applications. Okay, so these are the two drawback in the case of anisotropy. Okay, but in the case of randomly oriented, fiber also can be dispersed. Okay, randomly oriented one. So in that case, the mechanical property, okay, will be constant in all the 360-degree direction. That's why it is called isotropic material. Okay, fine. So this slide is indicating particulate-based composite. Maybe any form, particle form. Okay, plastics particle can be added. Some ceramic particle can be added. Metal particle can be added. These are the examples of the particulate ceramic, silicon carbide, boron carbide, titanium carbide, titanium boride. Okay, all are examples of the nano, not nano, that is ceramic powder particulates can be mixed with the matrix. Right. And one more point is the fiber size and the effect, okay, and the orientation will play a major role. Okay, so that's what we anyway just now we have discussed. Okay, suppose whenever the microscopic size range less than 1 micrometer, suppose if the size of the fiber is less than 1 micrometer. Okay, less than 1 micrometer mean up to 15% only we can add it. That's what energies already we have discussed. Okay, and we can get some improved properties. Suppose if it is greater than 1 micrometer, means we can add even 25% and more. So the point is, depends upon the size of the fiber, the percentage of addition of the fiber will be different. Right, now let us go to the nanocomposites. So you know very well. So nanocomposite mean what? Composite mean consisting of two phases, matrix and reinforcement. Any one of the material, the dimensions of any one of the material should be nano level. We can say it is called nano composite. Either a fiber particle may be nano or matrix particle may be, the grain size of the particle may be a nano. Okay, that is called nano composite material. Right. So here the matrix to nanofiller reinforcement combinations are very much important. And okay, and anyway, this nano composites are having potential application in food and packing industry, aerospace industry, so environmental protection applications, electronic industry, automotive engine parts, fuel tank. These are the major applications of nanocomposite. You see, so the important point is what I want to share here is whenever we want to synthesize or produce the nanomaterial or nanocomposites, the dispersions of the fiber is very much important. That is a very critical and very highly challenged one. Okay, so if you obtain the proper distributed fiber particle over the matrix, we can achieve improved properties. Otherwise, the property will be decreased. Okay, for example, you see this is some metal matrix, actually composite, aluminum magnesium alloy. Okay, these are all grains. These are all grain around 200 nanometer, around 200 nanometer, 200 matrix nanometer. And you see the block dot, okay, the red arrow indicate the nanoparticle, aluminum oxide, okay, and the blue color indicate the fiber form, aluminum carbide nanofiber form. It is the one examples of mathematics composite. This is the image obtained from the transmission electron microscopes. So we can see, so when we see this microstructure, almost all the nanoparticles and nanofibers are distributed uniformly. Obviously, we can obtain improved properties. And further, when we add the one more thing, percentage of addition of the nanoparticle over any metal, okay, during synthesizing, especially for ball milling, high energy ball milling, the grain size will be decreased. You know very well, the conventional material having very big grain. Maybe the size of the conventional grain, 1 to 2 micrometer. Okay, when we want to reduce the grain size, maybe 100 nanometer or 60 nanometer, or if you incorporate some of the ceramic particle, okay, still the grain size will be around 10 nanometer or 15 nanometer. My point is, by incorporating some nano reinforcements, the grain size of the bulk metal can be decreased. Okay, you see the green color indicate the nanoparticle. It is completely distributed uniformly. Some schematics. Okay, so the presence of this nano particle. Suppose after synthesizing the material by pressing or anything, we can make the product. And whenever we want to do the heat treatment, okay, you see this is a no reinforcement. Okay, this is also nanomatrix. This is nanomatrix. This is nanocomposite. This is mixed with the 12% of boron carbide. Okay, when we want to do the heat treatment, here maybe the grain may be grown. Okay, propagate, increases. But here, okay, during heat treatment, okay, or some elevated temperature, okay, the matrix grain will never propagate. Maybe little, okay. Why? The presence of nanoparticle, okay, it will be occupied over the grain boundary. Therefore, it will try to pin down or inhibit the growth of the grains. That's the benefit of nano materials. Okay, and you see, this is some interesting picture. High magnified, high resolutions, TM images. Okay, so you know very well, whenever you want to decrease the particle size, grain sizes, severe lattice distortions. Okay, the atomic, the structure of that, inside the atoms, okay, will be completely disturbed. Okay, so this is the composite, so copper lattice. So the line indicate d-spacing, angstrom level. D-spacing means the distance between the two atoms. Okay, and this is some boron carbide particles, and this is indicating some grain refinement. You see, a nano matrix material. This is the image obtained from SEM. Okay, some big grains are there, and here fine grains are there. So by means of the nanoparticle, introducing the nanoparticle, we can decrease the grain sizes of the matrix material. So by which the property can be improved. Okay, so that is the benefit of this ones. And types of nanocomposite. Okay, basically there are three nanocomposites. One is called mathematics nanocomposites, and the second one is called polymeric matrix nanocomposites, and the third one is called ceramic matrix nanocomposites. Okay, so within 10 minutes we'll try to finish it. The polymer matrix nanocomposite. Okay, so usually the polymer matrix nanocomposites, any kind of polymer, either the matrix from thermoplastic polymers or thermosetting polymer or elastomers or combination of these things can be used. You know very well, all the thermoplastic have linear and branched structure. Okay, so having strong intramolecular, that means among the atoms it can have good and strong, but the adhesive nature of the atom with the other particle will be very poor. That is very weak in intermolecular bond. That is the drawback in the thermoplastic material. But to improve the properties of the thermoplastic polymer, we can use nanocomposite. We can fabricate nanocomposite polymer matrix composite. Okay, so examples of them. Anyway, this thermoplastic, you know very well, it can be reshaped by application of heat and pressure. It will never harm the soil. Okay, it will never pollute the environmental conditions. Okay, so examples of the thermoplastic polymers are polyethylene, polypropylene, polystyrene, polycarbonate, polyacetal, polyamide. These are all examples of thermoplastic polymers. And the second one, thermosetting polymers. Anyway, now people are not using it. Still some application people are using this thermosetting polymer. Thermosetting mean what? Here during polymerization, especially here, condensation polymerization will be involved in the thermosetting polymers. So some byproduct will be coming out. Therefore, cross-linking will be formed. Okay, some network structure, complex structure will be formed. That's why all the thermosetting polymers cannot be reused, cannot be reshaped. When you heat it, it becomes decomposed and it can produce some tar. So examples of thermosetting polymers are epoxies, polyester, phenolics, urea formaldehyde, melamine, silicone. All are the examples of thermosetting polymers. Right. And one more interesting point I want to share with you is we have to note some of the important points whenever we want to synthesize the or use the polymeric matrix nanocomposites. Okay. So what is the point is? So for example, for comparisons, so in the micropolymeric matrix composites, when we add 5% of filler, 30 or 40 or 60% of property only can be improved. Whereas in the case of polymeric matrix nanocomposite, if you incorporate the same 5 but nano filler, here micron filler, here nano filler, if you incorporate 5% of nano filler, at least 2 to 3 times the properties of the matrix can be improved. That is the benefit of nano material or embedding of the nano reinforcement. Okay, right. And one more point is all the polymeric matrix nanocomposites have or provide large interface area because of the small particle size. Okay, and embedding of the reinforcement particle. There are lot of interface area between the matrix, that is called constituents. Between the constituents and mixed phases will be formed, by which only we can able to get the improved properties. The crack will never can able to propagate from one region to another region. Obviously, the creep property can be improved. Okay, right. So And that's why these are the things. And further, all the polymeric matrix nanocomposites alter the properties of the material. Already we have discussed. Okay, and further, according to the application, according to the functional requirement, we can define the properties of the polymeric matrix nanocomposites. Okay, and yeah, this is what already we have discussed. So since the polymeric nanocomposites are having more interfacial additions, okay, so the crack cannot be propagated, it will be slowed down. Okay, and further, the high surface area polymeric matrix nanocomposites can be applied in energy sectors as a catalyst, so battery capacitors, gas separation systems, filtering systems. Okay, and one more for example for you. Okay, if you take a single wall carbon nanotube, let us take a single wall carbon nanotube. It possesses 1 terapascal, unimaginable Young's modulus value, and even 500 gigapascal tensile strength can be obtained from a single wall carbon nanotube fiber. That's why the nanomaterials, nanofibers are playing a major role. And this slide is showing indicating the processing issues in nanocomposites. Okay, what are the processing issues which we have to follow? Okay, so usually, yeah, so whenever we want to incorporate the nanomaterials, okay, because of a large surface area to volume ratio, because of van der Waals force of attraction, agglomeration, clustering is the main phenomena. That's why we have to account these things. To avoid that one, it is always recommended to treat the fiber, to treat the nanomaterial, either by preheating or adding some coatant, surfactant, okay, by which we can able to get the uniform disposed reinforcement particle over the matrix. And one more thing is density issues. As long as reducing the particle size at the nano level, the density of the atom will be also decreased. So that means what? Lighter in density. So because of these issues, okay, it will be very high challenge to distribute the, even for example, ball milling. Okay, even if you use high ceramic balls during rotations, okay, because of light weight of the material, it will be very difficult to distribute the light density material uniformly. Okay, these are the agglomeration and density issues. These are the two issues we have to carefully handle during synthesizing the nano composite material. You see, I want to show you what is agglomeration. Agglomeration means clustering. You see, this is a picture of agglomerated clustering of the polypyrrole nanoparticles. You see, all are nanoparticles. Okay, the size is maybe less than 500 nanometer, and this is a titanium dioxide nanoparticle. You see, all are around 190 nanometer TiO2 particles. But you see, all are joined together because of van der Waals force of attraction. This is what agglomeration. So it is always it is a challenge to separate it. Okay, there are some techniques. Okay, fine. For example, this is the aluminum matrix particle mixed with the nano TiO2. So lot of clustering is there. But some other techniques, you see, this in the gray region indicate the matrix material. This is a nano titanium dioxide. You see here, all the nano titanium dioxide particles are uniformly distributed, embedded, okay, inside the matrix material. That's why we can achieve improved properties. So this is what dispersion, separation, okay, distribution of reinforcement over the matrix. Okay, and this is what I told you. This picture is example for how the interface addition. Okay, we know very well all the nanocomposites, okay, are having lot of interface additions. Because of this interface additions, okay, we can able to achieve good properties. Okay, you see, this is a high magnified TM images. Okay, you see one material, one phases. Okay, manganese, selenium. Okay, some is mixed with the some other copper lattice, sulfur lattice, selenium lattice. Okay, all are different material, different, all are atomic level. Okay, so I use this, it is my research work. Okay, and this is by which this is the interface. So because of presence of this interface, even somewhere crack formed. Suppose let us assume crack is formed in the copper matrix. Okay, because of this interface additions, okay, the crack, okay, will be restricted to another area. That's why the life of the component will be increased. Okay, fine. These are the major things. Practical experiences I am sharing you. Okay, right. And this slide is insisting what are the factor influences the properties of the polymeric matrix nanocomposite. These four things we have to keep in our mind. the surface modification of the filler and its interaction of the polymers, and filler volume fractions, and then aspect ratio, that means the diameter to length of the filler, and then filler alignment orientation. These are the 4 factors we have to account carefully, right? And this slide, I want to share this slide is what are the effective characterization techniques whenever we want to synthesize or examine the nanocomposite material. Okay, we should know as a researcher, okay, even for material design engineer, okay, any mechanical engineers, we should know the real-time application of these characterization tools. Okay, when you go to the industry, even for UG undergraduate student, when you go to industry, it will be helpful for you. So optical microscopes, some electron microscopes, these microscopes can be used to examine the microstructural analysis. Okay, that's a mistake. And for phase identification or for phase matching to determine the thermal stability of the material developed nanomaterial, nanocomposite, these techniques, X-ray diffractometer, X-ray photon spectroscopy, okay, or differential thermal analysis, or TGA, or some spectroscopy, either Raman spectroscopy or Fourier infrared spectroscopy can be used. So these are the common minimum tool we have to use it for examining the behavior of nanostructure, nanomaterial. Right. The last one is we would like to share about what are the synthesis of polymeric nanocomposite material. Please understand our topic is nanocomposite. It is related to polymers. Okay. So basically there are 5 potential methods are there for fabricating polymeric matrix nanocomposites, namely solution casting, melt blending, in situ polymerization methods, electrospinning, electro deposition methods. So let us discuss in a fast manner quickly with the pictures. So in a solution casting, it's very simple. Solution casting means nothing but, so whatever the matrix polymer. So here the polymer, now please understand, we are talking only polymeric matrix nanocomposite. Okay, so the matrix is polymer. Okay, either any thermopolymer or thermosetting polymers. Okay, the polymer should be mixed. Okay, we have to take the polymers, whichever the composite we want to fabricate it, and then it has to be dissolved in the solvent or solutions. Okay, usually the you know very well the melting temperature of the all the polymers around 200 or 250 260. Therefore, whenever we want to dispose the polymers for the any solution solvent, okay, either methanol or ethanol, okay, or toluene, okay, so we should not mix it at room temperature. For mixing, actually we have to use ultrasonic stirring. Okay, you know very well, ultrasonic stirring or magnetic stirring. These are the effective tool. Ultrasonic stirring means there is a chamber, there will be ultrasonic probe. Okay, this ultrasonic probe starts to vibrate. Okay, that means we have when we switch on the machines, okay, around 20 to 21 kilohertz, okay, amplitude will be acted on the ultrasonic probe. So because of these vibrations, okay, so the whatever the polymer we want to mix with the solutions, it will be disposed uniformly. But if you want to carry at a room temperature, okay, because of this high amplitude, okay, it will increase the temperature. That's why to minimize the temperature effect, so usually all the mixing dissolutions of the polymer over the solution solvent will be carried out under ice bath. So surrounding you have to place the ice bath. Simple setup only. Okay, simple setups only. And whatever the reinforcement you want to use it, it has to be dissolved the same or different in the same solvent. Okay, by means of the ultrasonic things. Then these two matrix and the reinforcement has to be once again mixed properly. Okay, during ultrasonic stirring. Okay, so because of high amplitude vibrations, high amplitude frequency, lot of teeny bubbles will be formed inside during stirring. Lot of teeny bubbles will be formed. Okay, so since the ultrasonic probe is giving continuous amplitude, and lot of bubbles are forming. Okay, more pressure will be built up inside the solutions. Once it reaches the critical value of the pressure built up, all the bubbles will be burst. During stirring, all the polymers chain will be moved here and there. Okay, whenever the bubbles are burst, okay, inside the polymers, okay, all the nanoparticles can able to enter. Okay, so at the end of the mixing, the ultrasonic stirring or magnetic stirring, okay, we can have the nanocomposite. So and keep on this one. Finally, after drying, okay, so people will do some degassing, drying. So we can have this some nano film or nano composite material, and we can do some pressing. We can in the form of film or rod form. What are the shape we want, we can do it. So this is a simple solution casting method. Okay, this is simple solution casting method. And each method has some own advantages. Okay, so we can have some greater film thickness can be obtained with accuracy of plus or minus 2%, and even 150 micron to 12 micron thick layer can also be formed from the solution casting. Okay, so solution casting very simple, just mixing the polymer and reinforcement. The mixing is important. Okay, right. Fine. And you see, so whenever the bubbles are formed, all the reinforced fiber will be entered between the matrix. This is called intercalcinations. During ultrasonications, intercalcinations will be involved during the thing. So intercalcination means entering of the fiber nanoparticle between the polymer matrix. Okay, this is what therefore the solution casted polymeric matrix composite always will have intercalcination structure. Okay, the second interesting method is melt blending methods. Okay, melt blending method. So very simple. So here, okay, so whatever the matrix material and whatever the reinforcement you want to fabricate, okay, so we have to do, people will do some pre-processing. Okay, both the precursor, okay, they will do some pre-processing, then they will mix inside the screw extruder. Like, it is like a injection. Okay, plastic injection technique, the same injection technique. Okay, so whatever the polymers, okay, this is low density polyethylene. So low density polyethylene. This is the graphene nanoparticles. So whatever the matrix and reinforcement you want to, we can mix with the you can charge over the hopper, and it will get inside the extruder. Okay, already there is a exchange heat exchange systems. Okay, and whenever the screw starts to rotate, okay, it will give lot of heat will be introduced, and due to which, okay, some all the the nanoparticle will be entered inside the matrix, so by which the composite can be produced. Okay, so during melt because of the heat and with the pressure, okay, and the gap between the two polymeric layer will be enhanced. Okay, so due to which more and more nanoparticle can be entered. Okay, this process, this is called, this phenomena, they are calling it as a exfoliation. So this they are calling it as a exfoliation. Okay, and this phenomena they are calling it as a exfoliation. Okay, exfoliation. Anyway, yeah, the exfoliation. Okay, so exfoliated structure will be obtained in the melt blending method. There are many things. You see, this is schematic. Okay, by which the same screw extruded can be used to produce some polyether ketone matrix and mixed with the multiple carbon nanotube composites. Okay, and this is another one. We can have some polyethylene tetraphthalic matrix reinforced with the cesium doped nanoparticle. So in the form of after rolling, after pressing, rolling, extrusion, different shapes can be obtained. Nanocomposite can be obtained. Okay, right. And the third one is called in situ polymerization technique. So in situ mean here, okay. So understand, already we know the proper mixing. Okay, the proper addition of the reinforcement particle over the matrix is important. That effectively can be obtained from the in situ polymerization techniques. Okay, so here by means of the chemical reaction, okay, we can able to mix Hardly 5 to maximum 5 minutes, sir. Till 5 or 10 minutes maximum. 5 minutes only maximum.
Okay. Okay. மணி அங்க கனெக்ட் ஆயிடுச்சான்னு கேளுங்க. சரி இருங்க மணி, நானே போயிடுறேன் இல்லாட்டே. ஹலோ விஜய் சார். ஹலோ ஹலோ இன்னைக்கு ஆயிடுச்சுங்க. இங்க ஏசி மெக்கானிக்கல் ஆயிடுச்சு வருது. இங்க கனெக்ட் ஆயிடுச்சா? அதான் தெரியல. இல்ல நான் இது பண்ணிருக்கா, க்ளோஸ் பண்ணிருக்கா? இங்கே கனெக்ட் ஆயிடுச்சு என்னமோ. நான் ஃபர்ஸ்ட் பண்ணதுனால இப்போ அவருது வர மாட்டேங்குதுங்க. டைம் பெரிய இதுல ஏமாந்துட்டோம். சார் சார்
Yes, sir. Shall I start, sir? Start பண்ணலாமா சார்?
So I think we can start, sir. இருக்காங்கன்னு நினைக்கிறேன்.
Okay, right, fine. Thank you. Right. So what we are discussing now, the second method, okay, the melt. Hardly maximum 5-7 minutes only we can finish it. And we are discussing now in situ polymerization. So here in situ polymerization, so they will add some surfactant, okay, some dopant, some initiator, reactant. So due to which the combination of during mixing, during stirring, either ultrasonic stirring or magnetic stirring, okay, the combination of intercalcinations and exfoliations will be carried out. Okay, because of intercalcinations, okay, so the nanoparticle can able to enter. Okay, and further because of the exfoliations, the gap between the two monomer will be enhanced, due to which more and more number of reinforcement will be entered. So this, because of this combination of intercalcinations and exfoliations, okay, we can produce nano polymeric matrix nanocomposites. The benefit of this method is, okay, most of the, actually we can have a very sound nanocomposite from the in situ polymerization technique. Okay, in situ polymerization, that means all the reinforcement will be completely impregnated for the given polymer. That kind of sound nano polymeric matrix composite can be obtained from the in situ polymerization. So this is the picture showing a production of nano graphene impregnated with the polystyrene. So polystyrene is the matrix. Okay. So first, in order to have layered structure of the graphene, okay, first, because of the nano graphene will have, because of lot of agglomerations, they have to heat it. Therefore, expanded graphene can be obtained. Okay, expanded graphene can be obtained, and that expanded graphene, okay, it has to be mixed with any solution solvent. Okay, using some ultrasonic scissor. Okay, then it will go for some water bath necessary, if necessary, to produce some emulsion, some micro emulsions. Here they will add some surfactant. Okay, so due to which the nano, okay, due to which the gap between the matrix will be increased. Okay, and layered polymers will be obtained. Okay, layered reinforcement will be obtained. That is called some coating, like that. Okay, and then again we have to introduce a polystyrene matrix. Okay, again we have to stir it. Therefore, the intercalcination and exfoliations process will be carried out. Okay, at 850 centigrade. Therefore, all the graphene nanoparticle will be entered inside the polyester matrix. We can get the composites. Okay, this is what in situ polymerization techniques. And the fourth interesting one is electrospinning method. Very interesting one. Okay, it's very simple, like a syringe. Very simple technique. Okay, simple and interesting technique. Okay, so in the fourth one is electrospinning. Electrospinning mean what? There will be a syringe, a pump. At the end of the pump, there is a syringe. Okay, inside the pump, so whatever the composite you want to produce it, so both the polymer solutions and the reinforcement should be mixed priorly, and it has to be charged inside the barrel of the pump. Okay, and then whenever you want to squeeze it, okay, at the end of the syringe, okay, the pressurized um, composite polymer solution will be coming. Okay, here this needle, okay, this wrench, okay, and there will be another collector will be there. There will be a roller, okay, or a disc, okay, to collect the nanofilm. Okay, and there will be collector and the needle, both will be connected to high voltage current. High potential should be introduced. Okay, right. How the nanofiber formed mean? Because of Taylor cone principle. Interesting phenomena. Taylor cone principle. So when you see the magnified view of the pin, okay, can have some conical shapes. Okay, right. Whenever you want to compress it, okay, compressed, okay, polymer solution, nanocomposite solution will be coming out. Okay, and at the front of the needle. At the same time, here we are introducing high voltage current, high potential. Okay, this high potential will try to, repels or oppose them coming solutions. Therefore, this nanocomposite solution will make some fiber form over the cone forms. Okay, depends upon the voltage potential, the fiber will be formed. At the same time, the collector will try to attract the fiber. Okay, it will be collected either film form or rolled form. If you roll it, we can get the continuous fiber. This is a fiber. So interesting method. Okay, but I mean, this is what electro spinning, and very simple method. This is our vertical one. Okay, the same method only. Okay, right. So here thin film can be collected, and here continuous fiber over the drum can be collected. Okay, this is what the electrospinning. And the last one is electro deposition, like a reverse electroplating technique. Okay, so this is also another one method, and by which we can synthesize the nanopolymeric matrix nanocomposites. Okay, basically there are at least two electrodes. One will be the working electrode. Okay, so where whichever the substance, whichever the matrix we want to coat, actually from the electro deposition technique we can coat them nanocomposite nanomaterial over the matrix. Okay, for coating application people are using electro deposition method. Here minimum there are two electrode. One is called working electrode. Okay, whatever the substrate work surface which you want to coat the nano precursors, okay, we have to connect it to the working electrode. The other one is called counter electrode. Okay, other charge. Okay, usually platinum. Okay, platinum will be the thing. Okay, it will be connected. It will be connected, and usually right. And for neutraling the some unwanted phases, there will be some reference electrode. Usually, silver and silver chloride will act as a reference electrode. When you give the high voltage current, okay, already whatever the precursor you want to coat for the polymers, it has to mix with the solutions. Okay, so if you establish the voltage current, okay, high voltage current, okay, depends upon the value. Okay, the precursors will be separated. It will be goes over the substrate. Coating will be carried out. So depends upon the voltage. Suppose if you substitute 5 million voltage, okay, per second, mean we can have mesoporous mesoporous structure over the fiber, or mesoporous mesofiber or nanostructure. Okay, depends upon the voltage. And you see, this is a carbon fiber, and this is a mesoporous nanoparticle over the fiber, and this is a mesofiber. Okay, this is a nanostructure. Okay, these are the objects. These are the coating obtained from the electro deposition. So my point is, there are 5 methods. So what these are the 5 potential methods: solution casting method, okay, so melt blending methods, in situ polymerization methods, okay, electrospinning, electro deposition. These are the 5 potential methods are being used in the industry in order to fabricate or manufacture the polymeric matrix nanocomposites. And now I would like to, within 1 minute, I want to share regarding the mathematics nanocomposite. If suppose if you have, there are a lot of methods are there. If you have next chance, we can discuss elaborately. Okay. So mathematics composite mean to increases the properties of the material. There are many mathematics composites are there. Many techniques are there, by rapid solidifications, vapor deposition technique, either PVD or CVD, electro deposition, chemical methods, or ball milling methods. Okay, there are many processing methods are there related to fabrication of matrix nanocomposites. Similarly, for ceramic matrix composites, some conventional powder metallurgy route, hot isostatic pressing, okay, or some polymer precursor route, PVD, CVD technique, some chemical methods, salt gel technique. Okay, these are the common processing technique used for or suggested for ceramic matrix nanocomposite. So anyway, this I don't want to touch. Okay, maybe next time if we have the chance, and we can discuss elaborately. Now we are focused only on polymer based nanocomposites. Okay, so these are the references. So thank you very much for your patience, and once again I would like to thank the management and principals for giving me an opportunity to share my experiences. My point is, as you are young, some faculty may be there, some students will be there. So everything you try to learn by experimental wise. Okay, so whatever the facilities available on you, you think and try to find the scientific reasons, and please spread your knowledge to our student community. So then only a lot of innovation will comes. Okay, our neighboring country. Okay, they are very strong in research. That's why they are very strong in technologies. Okay, so whenever the knowledge is going among everyone, okay, every people from their own angle, they can implement it. They can develop some new innovation. That means our country can get more benefits. Okay, so my point is, my intention is, you try to whatever you knowledge you gain, you try to share. Okay, and work hard. Okay, and everything will be good for you. There will be a good future for everyone, and we have to always keep on working. Okay, definitely we can achieve good things. So thank you very much. If you have any doubt, any questions, always welcomes, or you can mail me. Thank you.
Sir, thank you, sir.
Yeah.
It's a very informative session. On behalf of Arulmurugan webinar series, this is the first one conducting by mechanical department. For every week, every department will be conducting one. Next week, AME Industrial Safety Department is conducting one webinar. So the first meeting is a grand success. There are 599 participants have been applied, and that's why we have shared the links in YouTube and webinar WebEx. So both has been both sides. So we are very happy to have Dr. S. Shivashankaran has been explaining so many things. for the past 2 decades. We are having composite applications in various, and now we have very advanced technologies in composites, still young, and we have so many researchers going on in this field. So updations are made by our Dr. Shankaran, Associate Professor of Qasim University, Saudi Arabia. All his works have been completely shared over here. It is not the least time he cannot even share all these things, but at the maximum work he has done to make ourselves update the knowledge. Thank you for your kind commitment, sir. And also, I love to thank our correspondent, Dr. P.B. Kandasamy. He's a nice and personal, excellent personality. I cannot compare in my words. He has laid the platform for us to have this sort of series. And also, I'd like to thank Dr. P. Shanmugam, sir, our principal of this institution. He has applied his hands of experience in all these things. Without him, we could not able to consolidate all these things. We are very happy to convey my best wishes and thanks to our coordinators, Saramana Kumar, Vijay, and S. Karthik. They are the faculty member and other our mechanical department faculty members. Without their help, we could not have completed all these things. And we have all the participants from all over India. This is a very good participation. I could able to this thing, and we have shared the links in YouTube and WebEx. So without any already have some interruption, your patient is more thinking over here, and with a good patient, you have just listened to all these things. So as a head of the Department of Mechanical Engineering, Mohan Babu, I would like to thank you all for all the everything. Thank you once again. We'll meet you in the next session. Thank you very much.
Thank you, sir. Thank you very much. Thank you.
Thank you, sir.
Thank you, participants, for participating in this webinar. You can fill the feedback form which is posted in chat box. And if you are having any questions, you can unmute your mic and you can interact with the resource person. And participants in YouTube, you can post your comments, clarifications in chat box so that I can share with the speaker. Thank you. From participant side, any clarifications?
Good afternoon, sir.
Afternoon.
Sir, what is the main unique characteristics for electrospinning method among others?
Yeah, good questions. In the electrospinning techniques, okay, so we can produce, okay, functional, whatever the size of the nanofiber we want. Accordingly, we can control the thickness of the fiber. Therefore, depends upon the functional applications. Okay, so some layer we want some thickness of the material. We want to have more strength. Some material no need to have some strength. So that is called functional gradient material. Okay. So in that application, this electrospinning technique can be used. This is the main features. This is the main features of the electrospinning. I got my point. This is the main unique features for the electrospinning techniques. By means of the Taylor-Cohen principles, we can control, okay, effectively the fiber thickness. Yeah, thank you. Good questions.
Okay, thank you, sir.
Welcome.
Sir, any other clarification, sir? Sir,
There is
the
one
parties.
question. There is one question, sir. Even though I am adding surfactant to dispose, but some sedimentation is there. Yes, the sedimentation is the major issue. That's why you try to mix properly. You please create some ice bath. Even I'm not having that much experience on the I use some solution casting method for some of my work. Okay, my suggestion is okay. So you can use some ice bath and try to stir properly. So either by means of ultrasonic or magnetic stirring, so you can avoid the sedimentations. Yes, of course. Even whenever whenever I want to prepare some nanofluids for mixing of aluminum oxides, I faced this sedimentation issues. Okay, or you can reduce the volume fraction. You please try to reduce the volume fraction. There is a rule. Okay, so you try to follow it. So when you reduce the volume fraction of the fiber and the reinforcement, you can minimize the sedimentations. Good question. Thank you.
Dear participants, any other clarifications yet to be cleared by the resource person? I think it's over.
Yeah, thank you very much. Yes.
Yeah.
Thanks for everyone.
Yeah, thank you, sir. Thanks for the informative session. Thank you, sir.
Thank you, sir. Most welcome, sir. Right.
So thank you, Dr. Sivasankaran, sir. Thank you very much.
You're most welcome, sir. Most welcome, sir. Most welcome. Thank you.
Thank you,
Yeah,
sir.
thank you very much.
Thank you very much.
Right.
Dear participants, you will be getting the e-certificates through your registered mail ID within 3 days after filling your feedback form. Thank you. Now you can leave the meeting.
Okay, I will leave, sir.
Okay.
Sir? Thank you, sir. Thank you.
Okay. Thank you very much, sir.
Yeah, you're most.
Thank you very much. Okay.
Thank you.
Okay, thank you very much for your valuable information. Thank you.
Yes, most welcome, sir.
Okay.